In the last lecture, we have considered jointly distributed random vectors, in general a k dimensional or n dimensional random vector, and we in particular define joint moment generating function, and we proved an important property that if the random variables are independent, then the moment generating function of the sum of the random variables can be expressed as product of the moment generating functions of individual random variables. This last result is extremely useful in determining or deriving the distributions of sums of random variables. Let me illustrate by proving additive properties of certain distributions. So, firstly let us prove say additive property of binomial distributions. So, let us consider say x1, x2, xk be independently distributed random variables, and let xi follow binomial ni p distribution for I is equal to 1 to k. I am interested in the distribution of S, that is sigma xi I is equal to 1 to n, or rather we can call it Sn. So, if we use the MGF here, distribution of the MGF of the sum is equal to product of the MGF of xi's I is equal to 1 to n. Notice here that MGF of xi, that is q plus p e to the power t whole to the power ni, product I is equal to 1 to k. This is also k I is equal to 1 to k. Now, since the term is the same, the powers will be added up and it becomes q plus p e to the power t to the power sigma ni, which is the MGF of a binomial, which is MGF of binomial sigma ni p distribution. So, by uniqueness property of the MGF, Sn must follow binomial sigma ni p distribution. This additive property of binomial distribution can be expressed physically also. Here you can see that x1 denotes the number of successes in a sequence of n1 independent and identically conducted Bernouillian trials, where the probability of success is p. x2 denotes the number of successes in n2 independent and identically conducted Bernouillian trials with the probability of success p, and so on. Therefore, sigma xi can be considered as the total number of successes in n1 plus n2 plus nk independent and identically conducted Bernouillian trials where the probability of success is p. So, this physical fact is confirmed by this additive property, which we are able to prove here using the moment generating functions. Let us prove a similar property for Poisson distributions. So, additive property of Poisson distributions. So, let x1, x2, xk be independent Poisson random variables with xi having a Poisson lambda I distribution. Once again we are interested in the distribution of sigma xi I is equal to 1 to k. I think I made a mistake here. This should be Sk, that is sigma xi I is equal to 1 to k. So, here also it will be sum of k variables. So, by the independence we can use that the moment generating function of a sum is equal to the product of the moment generating functions. Now, moment generating function of a Poisson distribution with parameter lambda, that is given by e to the power lambda e to the power t minus 1. So, here for xi this becomes e to the power lambda I, product I is equal to 1 to k, which is becoming e to the power sigma lambda I e to the power t minus 1. So, once again if we use the uniqueness property of the MGF, we conclude that Sk follows Poisson sigma lambda I. That means sums of the independent Poisson random variables are again having a Poisson distribution. Once again we can see it in a physical terms. Here we are considering k different Poisson processes. X1 denotes the number of arrivals in the Poisson process with the arrival rate lambda 1. Xt denotes the number of arrivals in the Poisson process with arrival rate lambda 2, and so on. Therefore, sum of the xi's denotes the total number of arrivals in a Poisson process with the arrival rate sigma lambda I. Let us consider say a relation between geometric and say negative binomial distribution. So, let x1, x2, xk be independent and identically distributed geometric random variables with parameter p. So, we are considering Sk, that is sigma xi. Now, if I am looking at the MGF of Sk, now the MGF of a geometric random variable is p e to the power t divided by 1 minus q e to the power t, where q e to the power t is less than 1. Now, when we are multiplying it k times, this becomes power k, which is MGF of negative binomial with parameter k and p. So, this proves that sums of independent geometric variables with the same probability of success is negative binomial k p. Once again we can look at the physical interpretation of this result. X1 denotes the number of trials needed for the first success in a sequence of independently and identically conducted Bernouillian trials. X2 denotes the number of trials needed for the another success for the first time in a sequence of independent and identically conducted Bernouillian trials. Therefore, x1 plus x2 plus xk denotes the number of trials needed for the first time k success in a sequence of independent and identically conducted Bernouillian trials, and that we know that it has a negative binomial distributions with parameter k and p. In a similar way, we can prove additive nature of negative binomial distribution also. So, if I have x1, x2, xk independent negative binomials and say xi follows negative binomial with parameters say ri and p, I is equal to 1 to k, then if I consider the distribution of sk, that is sigma xi I is equal to 1 to k, then by this property when we are multiplying the moment generating functions, I will be multiplying p e to the power t divided by 1 minus q e to the power t to the power ri for I is equal to 1 to k. So, the exponent will become sigma ri, which will prove that the sum will follow a negative binomial distribution with parameter sigma ri and p. So, if the probability of success is constant, negative binomial distribution also follows an additive property. Let us look at a relationship between say negative exponential and gamma distributions. So, let x1, x2, xk, they will be independent and identically distributed exponential variables with parameter lambda. Now, let us consider the distribution of the sum. So, moment generating function becomes lambda by lambda minus t to the power k, which is MGF of gamma distribution with parameters k and lambda. That means, sums of independent exponential variables is a gamma variable. So, physically if we represent this result, if we are observing a Poisson process with rate lambda, x1 denotes the waiting time for the first occurrence, x2 denotes the waiting time for first occurrence at another point of time, xk denotes the waiting time for the first occurrence in a kth observation of the process. So, if we combine this, that is x1 plus x2 plus xk, we look at, that is when x1 is observed, we start observing the process once again, x2 is the time added thereafter, x3 denotes the time starting from when x2 has been, that is the second occurrence has been observed, then we observe. So, then x1 plus x2 plus xk denotes the waiting time for the first time kth occurrence in a Poisson process, and that we know that it follows a gamma distribution with parameters k and lambda. Likewise, we can prove the additive property of gamma distributions also. Once again, here we can consider say x1, x2, xk independent, and xi follows gamma say ri lambda, then sigma xi I is equal to 1 to k, that will follow gamma with parameter sigma ri lambda, because here we can consider xi as the waiting time for the first time rith occurrence in a Poisson process with rate lambda. So, when we add these timings, it means that it is the total waiting time for sigma ri occurrences in a Poisson process with rate lambda. Therefore, this gamma distribution also satisfies an additive property, provided the Poisson process parameter remains the same. In the case of normal distribution, we have much more general property. In fact, we have a linearity property. Let us consider say x1, x2, xk independent normal variables, and xi follows say normal mu I sigma I square for I is equal to 1 to k. Let us consider a linear function sigma ai xi plus bi, I is equal to 1 to k. Let us obtain the distribution of y. So, myt, that is equal to expectation of e to the power ty, that is expectation of e to the power t sigma ai xi plus bi. Here e to the power t into sigma bi can be kept out. So, it is e to the power t sigma bi, and then we have expectation of e to the power sigma ai xi and t. Now, this we can express as e to the power t sigma bi, and this term we can split. We can consider it as e to the power expectation of product e to the power sigma ai xi t. Now, here xi's are independent variables, therefore, this term is simply e to the power t sigma bi product of I is equal to 1 to k expectation of e to the power ai xi t. Now, this is nothing but the moment generating function of the random variable xi at the point ai. So, e to the power t sigma bi product I is equal to 1 to k moment generating function of xi at ai t. Now, xi's follow normal distributions, therefore, the moment generating function of xi can be written. So, we substitute that here to get e to the power mu I ai t plus half sigma I square ai square t square. So, after adjusting the terms we get e to the power t sigma ai mu I plus bi plus half t square sigma ai square sigma I square. Now, this we can identify as MGF of a normal distribution with mean sigma ai mu I plus bi and variance sigma ai square sigma I square. So, by the uniqueness property of the MGFs, this proves that y, that is equal to sigma ai xi plus bi, follows a normal distribution with parameters sigma ai mu I plus bi sigma ai square sigma I square. So, in the case of normal distributions, it is not only the sums, but any linear combination of the independent normal variables follows a normal distribution. Another important thing to notice here is that in normal distributions case, we can vary both the parameters. Earlier in the additive property of say gamma distribution, additive property of negative binomial distribution, or the additive property of binomial distribution, where two parameters are there, when we are considering several independent random variables, we were varying only one of the parameter, and one of the parameter was kept fixed in order to have the additive property. But in the case of normal distribution, we can vary both the parameters, and the property is also more general. Rather than just talking about the sums, we can talk about any linear function. There are certain results which are related to the calculation of the moments of sums, variances of the sums, etc. So, these I will state here. For example, if we look at say expectation of sigma xi, it is equal to sigma expectation of xi. If we are looking at variance of, now the proof of this fact is quite simple. You have to just apply the linearity property of the integral or the summation signs, because here it is expectation of a summation. So, either you will have a, if the random variables are discrete, we will have summations, or if we have continuous, we will have integral. So, when we apply the linearity property, then the sums can be taken inside and it will prove this property. In the case of variance, let us write for two of them, that is variance of say x1 plus x2. Now, this is equal to expectation of x1 plus x2 whole square minus expectation of x1 plus expectation of x2 whole square. So, this is equal to expectation of x1 square plus expectation of x2 square plus twice expectation x1 x2 minus expectation of x1 whole square minus expectation of x2 whole square minus twice expectation x1 into expectation of x2. So, this terms if we combine expectation of x1 square with expectation of x1 whole square, this is variance of x1. In a similar way, expectation of x2 square can be combined with expectation of x2 whole square, that leads to variance of x2. Now, this cross product term, that is expectation of x1 x2 minus expectation of x1 into expectation of x2, is nothing but the covariance term. So, variance of a sum is equal to sum of the variances plus twice covariance of x1 x2. So, there is an additional term here. Now, if x1 and x2 are independent, then covariance will be 0 and therefore, variance of x1 plus x2 will be equal to variance of x1 plus variance of x2. So, we can generalize this result, variance of a summation is equal to sum of the variances plus twice double summation covariances of xi xj, where I is less than j. Obviously, if the random variables x1, x2, xn are independent, then this covariances will vanish and we will have variances of the sum is equal to sum of the variances. We can also have a general formula for covariance of a sum with covariance of another sum. Say this is I is equal to 1 to m, this is j is equal to 1 to n. Then this is equal to double summation covariance of xi yj. That means covariance of each term in the first summation is taken with covariance with the term each term in the second. These properties are quite useful in calculation of the moments of the sums of distributions. We will consider a few multivariate distributions which are quite commonly used. One of them is a generalization of binomial distribution, the so called multinomial distribution. In the binomial distribution, we are considering a sequence of Bernalian trials in which each trial of the experiment results in two options. One is called success and another is called a failures. That is, two types of outcomes are possible. However, there are a variety of trials in which we may be interested in categorizing not only in two, but in k type of outcomes. So, for example, if you are looking at tossing of a die, then you have the faces coming up 1, 2, 3, 4, 5, 6. If you are looking at drawing a card from a pack of cards, then it could be any of the 4 suits, say heart, spade, club or diamond, or if you are looking at say whether what is the number on that, that is 1, 2, 3 up to 13. So, there are a variety of experiments where the possible outcomes can be more than 1. So, if the probability of ending up in outcome 1 is say P1, ending in outcome 2 is P2, getting an outcome k is Pk, and then if we conduct a certain number of trials say n, so out of that say x1 is the number of outcomes resulting in first type, x2 is the number of trials resulting in the second type of outcome, etc. What is the distribution of that? So, that is called a multinomial distribution. So, suppose a random experiment is conducted n times under identical conditions. Each trial may result in one of k mutually exclusive and exhaustive events. Let us call them say A1, A2, AK. Let Pj denote the probability of outcome Aj for j is equal to 1 to k. So, let us consider say x1 number of outcomes resulting in event say ai, xi denotes this for I is equal to 1 to k. Then what are the possible values of xi's? Xi's can take value 0, 1 to n, subject to the condition that sigma xi is equal to n, because n is the total number of trials. So, if we write down probability of say x1 is equal to x1, x2 is equal to say x2, xk is equal to xk, then this is equal to n factorial divided by x1 factorial, x2 factorial and so on, xk factorial, p1 to the power x1, p2 to the power x2, pk to the power xk, where n is equal to sigma xi, I is equal to 1 to k, it is equal to 0 otherwise. Now, if we look at this distribution here, if x1, x2, xk minus 1, that is any k minus 1 of these variables are given, the last one can be determined in terms of n minus the sum of the remaining ones. So, if we consider the joint distribution of a random variable say x1, x2, xk minus 1 with joint probability mass function given by this. So, we consider it as probability of x1 is equal to x1, x2 is equal to x2, xk minus 1 is equal to xk minus 1, that is n factorial divided by x1 factorial, x2 factorial, xk minus 1 factorial, n minus x1 minus x2 minus xk minus 1 factorial, p1 to the power x1 and so on, pk to minus 1 to the power xk minus 1, and then 1 minus p1 minus p2 minus pk minus 1 to the power n minus x1 minus x2 minus xk minus 1. If sigma xi I is equal to 1 to n minus 1 is less than or equal to n, 0 otherwise. This is said to have a multinomial distribution. So, in fact, if you look at these two, they are the same. So, but formally we define a multinomial distribution to be k minus 1 dimensional, because the last value is determined automatically. Like in the binomial distribution, we talk about the distribution of the number of successes. We do not say that distribution of number of successes and failures. Now, from a multinomial distribution, we can consider the joint MGF, the joint moment generating function of x1, x2, xk minus 1. So, it is evaluated at the point t1, t2, tk minus 1, that is expectation of e to the power sigma ti xi from 1 to k minus 1. So, if we look at this distribution here, now the sum of this is a multinomial, that is p1 plus p2 plus up to 1 minus p1 minus p2 minus pk minus 1 to the power n. So, the sum of this over all these combinations is actually a multinomial sum. So, if we want to calculate this term, it will become p1 e to the power t1 plus p2 e to the power t2 and so on, plus pk minus 1 e to the power tk minus 1 plus pk to the power n, and this is valid for all t1, t2, tk minus 1 belonging to rk minus 1. Now, easily you can see that suppose I substitute t2, t3 up to tk minus 1 is equal to 0, I will get p1 e to the power t1 plus pk to the power n, which will become actually the, so this pk is actually 1 minus p1 minus p2 minus pk minus 1. So, clearly we can see that m t1 0 0 0 is equal to p1 e to the power t1 plus p2 and so on plus pk to the power n, that we can write as 1 minus p1 plus p1 e to the power t1 to the power n. That is, x1 follows binomial n p1. That means the marginal distributions of xi's are binomial n pi for I is equal to 1 to k minus 1. In particular, we can talk about expectations. So, naturally expectation of xj will be n pj, variance of xj will be n pj 1 minus pj. We can also talk about the covariance terms between xi and xj, that will be minus n pi pj for I not equal to j, and therefore, correlation coefficient between xi and xj can be calculated to be minus pi pj divided by qi qj, where qi qj denotes 1 minus pi and 1 minus pj etc. to the power half for I not equal to j. So, the correlation coefficient between two of these can also be calculated. In particular, if in the multinomial distribution I consider k equal to 3, so I will have two of these variables, that is x1, x2. That distribution is called a trinomial distribution. So, that is a straightforward generalization of binomial distribution to the case when we are having three categories as the outcomes. So, it is called trinomial distribution. That is, for k equal to 3, the multinomial distribution is termed as trinomial distribution. So, if I say trinomial distribution, we can write the probability mass function as n factorial divided by x factorial y factorial n minus x minus y factorial p1 to the power x, p2 to the power y, 1 minus p1 minus p2 to the power n minus x minus y. Here x and y can take values 0, 1 to n, subject to the condition that x plus y will be less than or equal to n, and of course p1 p2 are greater than 0, subject to the condition that p1 plus p2 is less than or equal to 1. So, here if I look at the marginal distribution of x, that will be binomial n p1. If I look at the marginal distribution of y, that will be binomial n p2. Not only that, if we look at the conditional distributions of x given y and y given x, then conditional distribution of x given y is binomial n minus y p1 by 1 minus p2, and y given x has binomial n minus x p2 by 1 minus p1. Of course, when we write this p1 by 1 minus p2 and p2 by 1 minus p1, we are assuming that the sums are the number is between 0 to 1. So, this is one particular bivariate distribution, which is trinomial distribution, and a general multivariate distribution, that is a multinomial distribution. So, it is a generalization of the univariate binomial distribution. We have a couple of more generalizations. For example, we have done beta distribution. So, a beta distribution can be generalized as a bivariate beta distribution in the following way: f x y as gamma p1 plus p2 plus p3 divided by gamma of p1, gamma of p2, gamma of p3, x to the power p1 minus 1, y to the power p2 minus 1, 1 minus x minus y to the power p3 minus 1, where x and y are greater than or equal to 0 and x plus y is less than or equal to 1. p1, p2, p3 must be positive. Here we can see that the marginal distribution of x is beta with parameters p1 and p2 plus p3. In a similar way, marginal distribution of y can be calculated. It is beta with parameters p2 and p1 plus p3. The conditional distributions are also beta with a little scaling. For example, if I consider u is equal to y divided by 1 minus x, or v is equal to x divided by 1 minus y, then u given x is equal to x follows beta distribution with parameters p2, p3. If we consider v given y, that follows beta distribution with parameters p1 and p3. In no way this is a unique generalization of a beta distribution to two dimension. We can generalize in different ways also. What we are trying to see here is that the marginal distributions also have beta distribution. So, then in that case we are calling it as a bivariate beta distribution. A very similar thing is done for gamma distribution. So, a bivariate gamma distribution can be defined as fxy beta to the power alpha plus gamma divided by gamma alpha gamma gamma x to the power alpha minus 1, y minus x to the power gamma minus 1 e to the power minus beta y, where 0 less than x less than y, alpha beta gamma greater than 0. Here if we see the marginals, x follows gamma alpha beta and y follows gamma alpha plus gamma and beta. Also y minus x given x, this follows gamma gamma beta. So, this is another generalization of a univariate gamma distribution to a bivariate gamma distribution. We consider a bivariate uniform distribution. It is a discrete uniform distribution. So, consider probability of x1 is equal to x1, x2 is equal to small x2 as 2 by k into k plus 1, where x2 takes values 1 to x1 and x1 takes values 1 to k. For example, if we consider the points 1, 2, 3 up to k, then if I take x1 is equal to 1, then x2 will take value 1. If I take x1 is equal to 2, then x2 can take values 1 and 2, that is 1 and 2. If I take x1 is equal to 3, then x1 can take x2 can take values 1, 2 and 3. So, you can see that this distribution is a discrete uniform distribution with probabilities concentrated on this diagonals. This you can say it as the half of the square actually. We can easily see that the marginal distributions, if we sum over x2 from 1 to x1, this will give 2x1 by k into k plus 1 for x1 is equal to 1 to k. So, the marginal distribution of x1 is obtained like this. In a similar way, if we sum over x2, sum over x1 from x2 to k, then we get the marginal distribution of x2 as 2 into k plus 1 minus x2 divided by k into k plus 1 for x2 is equal to 1 to k. Important thing here to notice here is that if I take the conditional distributions of x2 given x1, it is a discrete uniform distribution on 1 to up to x1. Similarly, the conditional distribution of x1 given x2 is a discrete uniform distribution, univariate 1 by k plus 1 minus x2, that is ranged from x2 to k. So, this generalization of a bivariate of a discrete uniform distribution to 2 dimensions has the conditional distributions as discrete uniforms, but the marginals are not uniform. We can calculate certain moments about this distribution which can be obtained from the marginal distributions like expectation of x1, expectation of x1 square, variance of x1 and similar characteristics for the x2 variable. We can also look at the product moment here, that is expectation of x1 x2, which is calculated from the joint distribution of x1 x2, and after certain simplification it turns out to be 3k square plus 7k plus 2 by 12. So, covariance of x1 x2, that is expectation of x1 x2 minus expectation of x1 into expectation of x2. So, after simplification this quantity turns out to be k plus 2 into k minus 1 by 36. So, now if we divide covariance by the product of the square root of the variances, we get simply half, because it is k plus 2 into k minus 1 by 18 both of these. So, the value turns out to be half. So, the correlation coefficient between the random variables x1 and x2 is half here. We look at some application of the additive properties here. Let us consider here. Suppose the life of an electronic system is described as the sum of 4 independent exponential lives. So, y is x1 plus x2 plus x3 plus x4, and each of the xi's is exponential with mean life 4 hours. So, what is the probability that the system will operate at least 24 hours? That means we are interested to find out what is the probability of y greater than or equal to 24. Now, here we can use the additive property of the exponential distribution. We have proved that the sums of independent exponentials are following a gamma distribution. So, here each xi is exponential with parameter lambda is equal to 1 by 4. Here mean is 4, that is parameter lambda will be 1 by mean, because mean is 1 by lambda. So, y will follow gamma distribution with parameters 4 and 1 by 4. Now, the density of a gamma distribution with parameters 4 and 1 by 4 is given by 1 by 4 to the power 4 gamma 4 e to the power minus x by 4 x to the power 4 minus 1. So, we integrate from 24 to infinity. So, after some simplification, this value turns out to be 61 e to the power minus 6, that is 0.1512. That is, there is almost 15% of the chance that the system will be operating for at least 1 day. Let us look at one more application of bivariate distributions. So, consider an electronic device. So, it is designed in such a way that it switch house lights on or off at random times after it has been activated. Assume that it has been designed in such a way that it will be switched on and off exactly once in a 1 hour period. Let y denote the time at which the lights are turned on and x the time at which they are turned off. That means, firstly it will be switched on and then they will be switched off, and the joint density function for xy is given by 8xy for y less than x, and of course, since we are considering only 1 hour period, so both will lie between 0 to 1 and it is 0 elsewhere. What is the probability that the lights will be switched on within half hour after being activated and then switched off again within 15 minutes? That means, what is the probability that y is less than half and x is less than y plus 1 by 4, because within 15 minutes of getting on it should be switched off. So, x must be less than y plus 1 by 4. Now, to determine this probability, we look at the region of integration of the density. So, you see here the density is defined for, in a unit square, the density is defined for y less than x, that is this region. Now, here y less than half means that we are in the bottom region, and x is less than y plus 1 by 4. Now, x is greater than y, that means here, and the line x equal to y is equal to 1 plus 4 is this line. So, we are basically in this zone. So, we have to integrate the joint density 8xy over this region. So, the limits of integration are for x y to y plus 1 by 4, and for y it will be 0 to half. So, this turns out to be 11 by 96. In the same problem, let us look at what is the probability that the lights will be switched off within 45 minutes of the system being activated, given that they were switched on 10 minutes after the system was activated. That means, what is the probability that x is less than or equal to 3 by 4, given that y is equal to 1 by 6. So, we need the conditional distribution of x given y. So, firstly we look at the marginal distribution of y. So, here the joint distribution is 8xy, we will integrate with respect to x. Now, the region of integration for x is from y to 1. So, after integrating we get 4y into 1 minus y square, and therefore, the conditional distribution of x given y is evaluated as the ratio of the joint distribution divided by the marginal distribution of y, which turns out to be 2x by 1 minus y square for x lying between y and 1, where y is a value fixed between 0 to 1. So, the conditional distribution of x given y is equal to 1 by 6 is easily evaluated by substituting y is equal to 1 by 6 here, and we get 72 by 35 x for x lying between 1 by 6 to 1. Therefore, this conditional probability is obtained by evaluating the integral of this density over the region 1 by 6 to 3 by 4, and it is evaluated to be 11 by 20. Find the expected time that the lights will be turned off again, given that they were turned on 10 minutes after the system was activated. That means, what is the expected value of the distribution that we obtained just now, given y is equal to 1 by 6. So, the density is given here over this region. So, we calculate the expected value as integral of x into the density from 1 by 6 to 1 dx, and it is evaluated to be 43 by 63. Finally, in this problem, what is the correlation coefficient between the random variables x and y? So, in order to evaluate the correlation, we need the covariance term and the expectations of x and y and the variances of x and y. In order to evaluate the covariance term, we need the product moment. So, here expectation of x y is x into y into the joint density, that is 8 x y. Y is integrated from 0 to x and x is integrated from 0 to 1, which is 4 by 9. The marginal distribution of x is obtained by integrating with respect to y from 0 to x, which is simply 4 x cube. So, expectation of x turns out to be 4 by 5, variance of x turns out to be 2 by 75. The marginal distribution of y was evaluated here as 4y into 1 minus y square. So, we can evaluate the mean and the variance of y also. Therefore, we can find the covariance between x y as 4 by 9 minus 4 by 5 into 8 by 15, and the correlation turns out to be this divided by the square root of the variances of x and y, which is 0.49 approximately, that is nearly half. So, in this particular problem, the timings of switching on and the off of the lights is having correlation nearly half here. We have in general discussed the joint distributions, where we initially considered two variables, then we considered multivariate, that is k dimensional or n dimensional random variables. We have discussed the concept of marginal distributions, conditional distributions, the concept of correlations, and we have also discussed certain additive properties of the distributions. So, now in the next lecture we will see that if we consider transformations of the random vectors, how to obtain the distributions of that. So, in the next lectures we will be covering that topic. Thank you.